Okay, here we have a joint probability question. We've got a joint frequency table for 100 runners who are surveyed, and we've got a couple of things here. We've got the type of shoe here, and we have their mileage per week here, and then some questions about those things, about the probability that a runner will run 25 or more miles a week, and so on down in this section. But first things first, we need to total, get our marginal totals here. So we would add all of these up here and all of these here, and then the total is going to be 100. Okay, so that would be your first thing that you'd want to do when you have a problem like this. On the next slide, so we've got our totals here and along here, again totaling 100. Okay, so we've got the totals and our probability questions below here. So now that we've got these totaled up, and we can take a look and see what we've got here. Okay, so we're looking for the probability that a runner will run 25 or more miles a week. Okay, all right. So in this case then, we're looking at this row. It should probably say more than 25 miles a week. But that's what we're looking for, and so we've got there a total of 38 out of 100. So we would say 38 out of 100. 100 is 0.38. So there's a 38% chance that a runner in this sample will have run 25 more miles per week. Okay. What is the probability of a runner using Brookes shoes? Okay, so this is the same type of a problem, right? We're looking at the margins here. And so we've got Brookes shoes here, and we have 20 out of 100. So that's going to be 20 out of 100, and that's 0.2, or a 20% chance that a runner will use Brookes shoes. Okay, so this is your sample, and you could say, well, if this sample is representative in a random sample, that's what we would expect, or that's what we might be able to expect. Okay, all right, from an overall population, that is, as far as our expectations. Now, part C. What is the probability that a runner will run less than 15 miles per week or use Brookes shoes? Okay, so with an or probability, we will add probabilities together, and then we have to subtract where they overlap. Okay, so we've talked about this in class. So we've got a couple of areas we want to look at now. That is less than 15 miles a week right here, and Brookes shoes, which you already looked at. So we would have 20, right? So I'm taking the Brookes total, and then 25 plus 25. So we're adding again in this or probability, and then we want to subtract out where the overlap is, minus 5. Okay. Over 100, so we would have 40 over 100, or a 40% chance that a runner will run less than 15 miles a week or use Brookes shoes. Okay, so that's the couple of things there, right, on the probability rules. We're adding when we've got an or, and then when you've got a joint probability table like this, you have to subtract out any overlap where they're both the less than 15 and the Brookes shoes, okay, or otherwise we'd be double counting. All right, or over counting, maybe not double, but over counting. All right, and now here we've got the last part, which is if a runner uses Nike shoes, what is the probability that he or she runs 25 or more miles per week? Okay, so this is the probability of more than 25 given Nike, okay, and so in this case, right, since that we're given that it's Nike shoes, right, given that it's Nike, then our attention turns from our sample of 100 to this group of 35. So that becomes our denominator then. So we're given, we already know it's somebody who's using Nike. What is the probability that it's more than 25? So in that case then we have 13, right, I'm looking at this one, more than 25, over 35. Okay, so then our probability becomes just over 37% that the runner using Nike shoes, or given the runners using Nike shoes, that they're going to run more than 25 miles a week. Okay, so that's a conditional probability, right? So when we're given that condition, right, that changes some of the way that we calculate. We can still use the same information, but it changes how we look at that, and like I said, our denominator. All right, so that's our joint probability problem.